Hey, what's up YouTube? Welcome to another video. So I'm not sure if I uploaded this before. I definitely have this video in Spanish, but I went and watched it in Spanish and definitely I did not like the explanation that I had before. So I'm gonna redo this video and hopefully clear some things up. So the problem is called coin change, and essentially you're given an integer array of coins representing the different number of coins that you have in order to get desired or target amount. So it says return the fewest number of coins that you need in order to make up to that amount. So essentially make the most efficient solution. If the amount cannot be made up by any coin combination, return -1. And in the example here, you have 1, 2, 5, and the amount is 11. So you can see that the most efficient way to get an 11 is 5, 5, and 1, right? Because you can probably get it, with 5 2s and then a 1, but obviously that's not the most efficient. So 2 5s and a 1 is the most efficient. And then you have example 2, where you only have 2 unit coins, or a coin worth 2, whatever, and the amount is 3, so that's not possible. Therefore, the output is -1. And so how many coins do you need in order to get 0? Well, in order to get 0, you need 0 coins. So the output actually is a valid one, which is 0 and not -1. And the way they show the example is actually very I don't know if conspicuous is the right word, but they do this on purpose. So you have to make sure that you're thinking of this and accounting for this. So I have this here, coin change, and let me see if I can make this bigger. Right, so this is the example. But there's a caveat here. Probably the first thing that you think is, this seems very simple. I'm just going to, do a greedy algorithm, trying to get the most amount without overpassing 11. So I'm going to do, 5. Is that larger than 11? No. 5. Is that larger or equal than 11? No. 2. So I have 10. Is 10 plus 2 larger than 11? Yes. Okay, move on to the next one, and so on and so forth. There's a problem with this, and that's why this is not the solution, is that, and of course they're not going to put this in the description, because whoever is testing you on this wants you to realize this and know that whatever you were thinking as a greedy solution is not the right one. So I'm going to put up an example here with 1, 3, and 4. And the amount, I'm going to make it 6. So notice how now things change. See how now 4, so if I choose one coin worth 4, is that larger or equal to 6? No. Okay, so how about now if I choose 3? Yeah, that goes over, that's 7. Then I choose 1, that's 5. I choose 1 again, that's 6. And like the amount or the combination of coins, solution, I'm going to put underscore W, meaning wrong, would be 1, 1, 4. And you can tell right away, obviously, that the most efficient solution is a 3. So then you go like, okay, so definitely this is not the correct solution. So what is it that you can do in order to get the correct solution? Well, the second thing that you have to realize, and I was doing some pseudocode here, but realized that was not really helpful. What you need to realize is the following. You can do, in order, and I'm going to do the example with this particular example, the 1, 3, and a 4, right? That way it's not too hard, because then problems can get, if I do 11, there's 11 choices at some point. But with 6, so let's say that you have, from your choices, you have a 1, a 3, or a 4. So let's say you choose 1 and you choose 1. So you can go ahead and choose 1 6 times until you get 6. Or you can choose 3 and then 1 and then 1, right? So 4, 5, and 6. Or you can choose 3, 3, and then you're done. Or you can choose 4, 1, 1. And then, so the number of correct choices that you can have here are, well, with the 1 can actually be, you have 1, 3, 1, 1, or 1, 1, 3, 1131. You get the point, right? So there's multiple choices where you get 6, you know, going by this route, or choosing like 13 or 113 or 1113, etc. So, and by the way, this doesn't get as nasty because the amount is low, but with 11, the number of possible combinations, it's even more. And what you have to realize here is that you're repeating work. So how do you realize that you're repeating work? Well, let's go with the 6 and not with 11 again. So one possible choice is you do 1 1, and I'm gonna choose a 3 just to save ourselves like some time. So that's 5, and then the last one, right? Well, this would be to the right actually. So this would be here, that would be there, and then you would choose 1 more time. Sorry, this is A1. Excuse my poorly drawn ones. But then that would get you 6, agreed? This is exactly the same as saying 1, then 3, then 1, right? So we have the 5 there, 1. Because the number of combinations is exactly the same. They're just in different order. And same thing if you choose, you know, 1, then 1, again, Jesus. Okay, that's a very poorly drawn one. So 1, 1, 1, and you get the gist. So these are the same. So what can we do? Well, since we are redoing the same computation, like we know that 3 1s and 1 3 is the correct answer to get a 6. Not the most efficient, but it's a possible answer. We don't have to repeat this. So what can we do? We can memorize essentially compute and save that computation somewhere. So what we can do is I believe it's bottom up, but essentially tabulate or compute and save our calculations. So I'm going to be doing the following. I can leave that there, and I can bring this to the bottom so we can see what we need to compute, or better yet, I'll just copy and paste this. All right, so I'm going to put all of this here. Okay, joke's on me. There you go. So what can we do? So in order to get 6, what we do is we computate this, and this is going to be our dynamic programming, or we can put cache or whatever. You normally see DP, but either or is fine. What we are going to do is compute how many coins do we need in order to get a specific value prior to getting the full amount. So what do I mean by that? So let's say how many coins do we need to get 0? Obviously 0. Therefore DP0 will always be 0. Something very important. All of this we need to initialize to. So I'm going to put DP1, DP2, DP3, all the way to 6, and I will write all of this down. DP5, DP6. So again, all of these are equal positive infinity because we want the biggest value in the positive direction. Which, by the way, in Golang, actually you use max integer of 32 bits. I'll explain later why. But since you can do this in Python or any other language, positive infinity is fine. And there's a reason why. Obviously, you want to get the minimum value of 2. So, you know for a fact that since this is the max value, whichever other number you put compared to infinity, that would be the minimum value. That's why we use infinity. So what I'm going to do is the following. I'm going to start with coin 1, and I'm going to paste these values. I'm going to put them over here. So what's DP1? DP1, so you're going to iterate through the coins, right? And the way that we're going to be solving this is I is going to be assigned to the coin value, and you want to make sure that you can get the minimum of dpi, which I'm going to put coin 1. So in this case, coin 1 is just dp1, or dpi minus coin plus 1. So why do we want to do this? Let's say that we're calculating something different, and let's say that we're using a bigger coin. If we use a very bigger coin, I'm trying to see if this is useful right now, but essentially, I'm trying to think if this will be useful right now. Actually, no, never mind. Not a bigger coin. So essentially, when we're doing a loop, first we assign it to the coin, and then we increment plus plus. So I'm going to say like I is equal to coin, and then I plus plus. So right now, this is going to be equal to 0, of course. But let's say I'm going to get rid of this, and I'm going to put the minimum. Let's say for round 2, it would be dp2, or it would be dp2 minus 1. There you go. Which, you know, this ends up being dp1 plus 1. And so this is precisely, and I'll put this back as so, coin, which in this case we know the coin is 1, right? So we have coin is equal to 1, I is equal to coin, and then in the loop we increment I. Okay. What is the 1? The 1 signifies that at least you need the coin itself. So what does that mean? What is dp1? So you're going to be looking previously where dp1 was computed, which in this case it was just initialized to infinity. Therefore, this infinity, and it's you know, infinitely big or positive. Hence, this is just too big. And then I minus, in this case, 1. So 1 minus 1, which is dp0. In this case, dp0 is just 0, and 1 is, you know, the coin 1 itself. Therefore, this becomes 1. We do the same thing with dp2. So dp2 here is just, you know, positive infinity. 2 minus 1 is just dp1. So dp1 we said prior that now is 1, plus 1 is just 2. So then now here we put 2. And we do the same here with dp3. So previously dp3 was just positive infinity, or we have 3 minus the coin, which is 1, which would be dp2. And dp2 is, you know, 2. So 2 plus 1, 3. And essentially you can tell that since this is the coin 1, all of these are going to be equal to, you know, dp4 equals to 4. And I'll change this to 4. dp5 equals to 5, and dp6 equals to 6, right? So let me just write that down. And I know that I'm being very thorough, but hopefully me being very thorough will help you understand this. And this is a4, this is a5, this is a6, dp5, dp6, right? So all of this would be whatever the amount equals, because we're using, okay, how many coins of 1, sorry, do we need to get a 6 coins? Makes total sense, right? Nothing too complex here. But now we are going to then go to the next iteration, and then our coin out is going to be equal to 3. And let me make a space for clarity. And I'm actually going to copy all of this, and then we'll change it. Let me move this here. Okay, I guess I'll make a new text. Yeah, let me see if I can move it. Okay. Okay, so now we're going to delete this because obviously these are not correct anymore. And since by the way, since we're using coin 3, we already know that we cannot get 1 or 2 by doing this calculation. So we can automatically say that, you know, 1 stays as 1, 2 stays at 2. And then you go straight at 3. So previously, what was dp3? So we know that dp3 is 3. So what's the minimum between that or dp3 minus coin, which is, 3. So dp3 of minus 3 is dp0, so 0 plus 1. Remember, the 1 signifies the coin itself of 3, of course. So here we just put 1. Same thing we do with 4. So dp4, which is 4 previously, right? 4. Or dp of 4 minus 3, which is dp1 plus 1. So dp1 is 1, and then 1 plus 1 is just 2. So in this case, we have 2. Then we go to 6. dp5. So dp5 previously was 5. So what's the minimum between 5 or dp of 5 minus coin, which is 5 minus 3 is 2. So dp2 is 2. So 2 plus 1, 3. So we're going to put 3 instead of 5. Then dp6. So dp6 was 6 prior, and then dp6 minus coin, which is 3, is dp3. So if we go to dp3, which is 1 plus 1, now is 2. And am I missing one more coin? I think we have, 4. We're missing the 4. So now the last round is going to be with a 4. And we'll see here how the 4 is actually not the most efficient to get 6. So coin here is 4. Then I'm going to go ahead and copy all of this, get rid of what we don't need to compute. And I just realized that I was covering, okay, here are the answers. Maybe I was covering a little bit of the answers, but here are the answers. Okay. So let's go ahead and do this. And same thing with 3 and 4. Actually, we can compute it. But again, since coin 4 is bigger than 0 to 3, we don't need to compute those again. So previously, dp4, we had that it was 2, right? Because I'm referencing this. Another way, I'll delete this so I don't confuse you guys. dp4 was 2, but in this case, dp4 2 or dp4 minus 4, which is 0 plus 1, is just 1, right? Because of course, with 1 coin, we get the amount of 4. dp5, we have that previously was 3. Now we have 5 minus 4, which is dp1, so 1 plus 1 is just 2. And, this is more efficient than the previous dp5. And then dp6, we have that previously, it was 2. So 2, a minimum of 2, or dp6 minus 4, which is dp2 plus 1. dp2, which is 2 plus 1 is 3. And previously we had just 2. So instead of changing this to 3, of course, we're going to leave it as 2, because 2 is the most efficient amount of this 2, or the minimum value of those 2. So then if the amount is 6, we just have to return dp amount, which that will equal to 2. And that is how we compute the answer. And we'll code it right now. Now, if for some reason, let's say that you're computing, but let's say that there's no solution, you're gonna have infinity. And then here, when you do dp amount, you check that you're not returning infinity. So you'll see right now when I code it. So I'm gonna be doing this with Golang because you guys have to ask for some Golang programming. So let's go ahead and do that. And I'm gonna be doing the following. dp, I'm going to initialize my slice to a slice of integers. I'm gonna put a length of amount plus 1, because remember, 0 doesn't account for all the coins. We'll have to put all the way from 1 and 6 plus the 0 index, therefore amount plus 1. The next thing that we want to do is put the infinity inside of the slice. So I'm going to do for I, I'm going to range through the amount. I'm going to do dpi is equal to math, and pay attention to this. I'm going to put max integer 32. Why do I put max integer 32? especially with infinity, I think in Golang infinity gives like an error. You can use that with Python and JavaScript, and you won't have a problem. But with Golang, you do seem to have a problem if you do. There's like, I didn't want to delete all of it. If you do inf and you put 1 for max infinity, and by the way, so that's a float 64, so you have to convert this to an int. And then here you add that. I think this still will give you an error, so that's why I used max in 32. You can even use uint, so unsigned integer, and that will give you a right answer. And you can see that you can use 32 bits because here is 2 to the 31. So that's essentially 32 unsigned bits, possible combination of numbers or bits. So that's how you know you can use this. But this also works, but you can use uint, whichever you rather. Now dp0, we know that it's 0, so we want to also make sure that we have that, because prior we would had this, and then we can move on with our solution where we can iterate through each coin. So for each coin, as we did in the example, range through the coins that we have, right? So for each coin of coins, or for each coin in coins, we want to do the following. We want to assign I to the coin amount, and then as long as as long as I doesn't go over the amount, we are going to increment I. And what we're going to be doing is dpi will equal the minimum of, as we said before, dpi or dp of I minus coin plus 1, where again the 1 signifies the coin itself. And then if everything goes right, well, not return, we don't have ternary in Golang, but you would do if dp amount is equal to max int 32, then, and this does have to be like this, return -1, because there's no solution. Otherwise you return dp amount. And for this, you just create a quick function. There's already built-in functions in Golang, but I don't think Leetcode has this. So if a is less than b, return a, otherwise return b, and that's it. And let me get rid of this so you can see like the solution. I can actually like make this a little bit smaller. So that's the complete solution. I know that this can be annoying in Golang to have that auxiliary, but again, there's a min function and sort functions and whatnot in Golang already built in. It's just that I don't think the Leetcode compiler has it. So I'm gonna run this, and I have a mistake. Range cannot range over amount variable type int. Oh, sorry, dp, not the amount. Which I think we'll be able to do that in Golang 1.22, but anyway. So the solution is fine. I ran the code and now I submitted it. It's 9 milliseconds. It ranges between 3 milliseconds and 11 milliseconds. Honestly, it's not really important. The important thing is that this is a dynamic programming solution, which is one-dimensional bottoms up. Or bottom up, yeah, bottom up, or top bottom. Anyway, the one-dimensional dynamic programming. So hopefully with this you have more clarity on how this works. If you like this video, give it a like, subscribe, and I'll see you on the next video.